Hello, today we are going to start with a new topic, colloidal state. Whether we are aware or not, they have become an integral part of our daily life. The toothpaste that we use, the milk that we drink, the butter that we apply on the slice of bread, the muddy water that comes into the municipal taps, and also the paints that we apply onto the walls are all examples of colloidal state in action. It will be interesting to talk about various aspects of colloidal state. In today's lecture, I'll introduce you to the colloidal state. What are crystalloids? What do you mean by colloids? We will look at colloidal substances or colloidal state. We will try to resolve that controversy. And then we look at the characteristics of true solutions, colloidal dispersions and suspensions. Classification based on physical state. What are the terms dispersed phase and dispersion medium mean? Based on that, how we classify the colloidal state as sol, solid sol, aerosol, gel and emulsion, foam and solid foam or froth. Another way of classification based on interaction, lyophilic sols and lyophobic sols, and then we have third way of classification based on type of particles, in which we will see what do we mean by multimolecular colloids, macromolecular colloids and associated colloids. Then I will summarize what we have studied today. It all started with the work of Thomas Graham. You are familiar with the name of the scientist. He is the one who studied diffusion of gases through porous spots and through orifice, and he found a relation between the rate of diffusion or effusion and the density of the gases, and he came out with what is called Graham's law of diffusion. But his work, in which he studied the behavior of solutions through animal membranes, is extremely important. The result of this study is the discovery of dialysis or the dialyzer, as he coined the term. Because of this contribution, Graham is regarded as the father of colloid science. Let us look at the Graham's observation. While studying the behavior of substances in solution with regard to their diffusion, he made important observations. In one of the experiments, he took a colored sugar solution in a glass and poured water from the sides very slowly to fill the glass. He observed that it took a long time for the color to reach to the top of the water level. That means to spread that color upwards so that the solution becomes uniformly colored. Further, he studied behavior of substances like sugar, common salt, urea, how they diffuse through the animal membrane. He found that these substances easily diffuse through, that means they easily pass through these membranes onto the other side. Whereas substances like gum arabic, glue, gelatin, he found that they don't diffuse through the animal membrane. That led him to classify the substances into two categories, crystalloids and colloids. What do you mean by that? What are crystalloids? According to Graham, crystalloids are those substances which are crystalline in nature and whose solutions are able to diffuse through the animal membrane easily. The examples are the same that we saw earlier. The crystalline sugar, common salt, urea, they are all crystalline, we know that. Colloids, on the other hand, are those substances which are amorphous in nature and are unable to diffuse through the membrane. The examples are gum arabic, glue, gelatin, which are all glue-like, non-crystalline substances. How he came to this term colloids? Greek word kolla means glue-like, and these substances which diffused very slowly through the membrane or did not diffuse through are called colloids. So, Graham soon realized that the classification of substances as crystalloids and colloids was not correct. What made him to change his mind? Because many substances which are crystalline, like sulfur, graphite, sparingly soluble salts, can be obtained in colloidal form. In fact, a colloidal system can be generated from almost any substance. Now we know that X-ray diffraction studies confirms that particles in a colloidal system are often crystalline in nature. Therefore, it is not the property of the substance, it is the state in which these substances are existing when they are added into a medium. We are familiar with the classification of matter into three states: the gaseous state, the liquid state, and the solid state. Because of the interesting properties shown by substances which we called colloids, it is now accepted that colloidal state can be considered as the fourth state of matter. Remember, it is the colloidal state and not colloidal substance. Substances are not colloidal. Substances can be brought into colloidal form by various techniques. So, in this state, substances exhibit unique properties because of the small size of particles. It is the particle size that decides whether the substance is a colloid or not. Certain substances could behave as both crystalloid and colloid under different conditions of preparation, depending on the size of their particles. Crystalloids form smaller particles in solution and colloids form bigger particles relative to the pore size of the membrane, making diffusion difficult or impossible. It is just a sieving action. The pore size of the membrane are much smaller than the particle size of the substances which are termed colloids. So, we can try an experiment. If we add substance to three different beakers containing, say, water, what happens? In the first case, the added substance may dissolve completely in water, disperse to the atomic, molecular or ionic level to give what is called a true solution. On the other hand, the added substance may remain suspended in water and after some time slowly start settling down under gravity at the bottom of the beaker. But there is the third possibility where the added substance does not go to the molecular or atomic level, instead of that forms smaller aggregates of that substance, where you have multiple molecules or atoms or ions together, and may not be visible to the naked eye, and they remain suspended there, giving rise to what are called colloidal dispersions. So, it is shown in the figure here. It is the size of the particle that decides whether the system that is formed is a true solution or a colloidal dispersion or a suspension. Particles of the substance are present in solution as atoms, ions or molecules. That means their size is less than 1 nanometer in true solutions. They are homogeneous one phase systems. These are the terms you have come across earlier. The particles are not visible to the naked eye and not even under a microscope. They will pass through easily through a filter paper, and they will also pass through an animal membrane equally fast. Examples are again sugar, salt, urea, which form true solutions in water. We have experienced that in the lab. In the case of colloidal dispersions, the particles of the substance go to the level of 1 nanometer to about 1000 nanometers, and in literature you may find that the upper limit is just 500 nanometers. These are maybe aggregates of atoms, ions or molecules falling in the size range that I just mentioned. Because the particles and the solvent, the particle sizes are different. They are heterogeneous systems. They are two-phase systems. The particles are not large enough to be visible even under a microscope, and they will pass through ordinary filter paper easily, but not through animal membranes. Examples: glue, gum arabic, gelatin, they form colloidal dispersions in water. The characteristic properties of these systems can be tabulated here. In the table you can see the properties that we just described: particle size, nature, visibility to the naked eye. The appearance, if you look at, the true solutions are transparent, colloidal dispersions are generally transparent, whereas suspensions are opaque. Filtrability we have seen, easily they pass through animal membrane and definitely through filter paper. Here passage through filter paper is unhindered, whereas through animal membrane it is prevented. And in the case of suspensions, particles are large enough so that they do not pass through both the filter paper as well as the animal membrane. In the case of true solutions, the gravity settling is not possible. That is true even for the colloidal dispersions, but in the case of suspensions, gravity is able to settle the particles to the bottom of the vessel. We have already seen the diffusion, that property that distinguishes true solutions, colloidal dispersions and suspensions. And one interesting property that we can now look at, the scattering of light. The atoms, molecules and ions are too small to scatter light, whereas the colloidal dispersions are able to scatter light, and we will see that when we discuss this aspect, what is known as Tyndall effect. Even suspensions may exhibit the so-called Tyndall effect. Therefore, we can say that a colloidal dispersion is neither a solution nor a suspension. A colloidal dispersion is a heterogeneous system that consists of a dispersed phase, that is a discontinuous phase, and a dispersion medium, that is a continuous phase. And colloidal dispersions can be classified on the basis of the physical state of the dispersed phase and the dispersion medium. Now, the physical state can be gas, liquid or solid, any combination of the two, like liquid-liquid, solid-liquid, solid gas, except gas-gas system. Reason being, the gases are completely miscible in each other they give a homogeneous system. Take for example the milk. It's an example in which the fat globules are dispersed in water. The fat globules form the dispersed phase and water is the dispersion medium. We use the term sol in the case where we disperse a solid in a liquid, solid, or even in a gaseous medium. The classification based on physical state of the dispersed phase and the dispersion medium can be seen in this table. If we have a solid-solid combination, it is a solid sol where gems, ruby, glass, minerals, etc. are the examples. If it is solid liquid, it is simply sol. We can have gold sol, sulfur sol, muddy water, ferric hydroxide sol as examples. Similarly, if the gas is the dispersion medium and we put solid into it, it becomes aerosol. The smoke is the example of it. If the liquid is the dispersed phase and solid is the dispersion medium, we get a gel. The name gel talks about jelly materials. Even curd and cheese are examples of gels. If you have liquid-liquid combination, the resulting system is an emulsion. Milk, water in benzene, the cream that we use are all examples of emulsions. The liquid-gas combination is liquid aerosol. The clouds, fog, mist are examples of this. If gas is the dispersed phase and solid is the dispersion medium, we get the solid foam. The lava, the pumice stone, even the so-called thermocol is an example of such a system. And gas in liquid as the dispersion medium is the foam. The soap bubble, for example, the froth that you get is an example of that. Here are some pictures which will help you to test your knowledge on this classification. You can try to identify each one of these photographs with the terminology that you have used as sol, aerosol, emulsion, gel, etc. There is another way to classify the colloidal systems based on the interaction between the dispersed phase and the dispersion medium as lyophilic sols and lyophobic sols. The lyophilic sol means liquid loving or the solvent loving. Some substances have an affinity for certain liquids, and when they are mixed, they readily form a colloidal dispersion. They are called lyophilic colloids or intrinsic colloids. The sols can thus be formed and termed lyophilic sols. When water is used as the dispersion medium, such colloids are called hydrophilic colloids or hydrophilic sols. Examples: starch easily forms a lyophilic sol when shaken with hot water. There are other examples: sols of proteins in water, sols of polymers in organic solvents, the latex that oozes out of the rubber tree when we pierce it. Since the dispersion medium and the dispersed phase have love for each other, lyophilic sols are stable and do not require a stabilizing agent. That means they cannot be precipitated easily. An important characteristic of these sols is that if the dispersed phase is separated from the dispersion medium, say by evaporation, the dispersed phase can again be brought into the sol form by simply shaking with the dispersion medium. Therefore, lyophilic sols are also called reversible sols. Lyophobic sols, on the other hand, are the ones in which there is no affinity between the dispersion medium and the dispersed phase. Solvent hating or liquid hating systems. If you want to prepare these salts, you have to use special methods. By simply shaking the dispersed phase substance in the dispersion medium will not result in a salt. So, we can look at some of those special techniques when we take up the preparation of colloids. And because of this, they are referred to as extrinsic colloids. If we use water as the dispersion medium, they are called hydrophobic salts. Examples are salts of metals such as gold salt, platinum salt, and salts of insoluble substances such as sulfur, metal sulfides, and oxides. Lyophobic salts are relatively less stable as compared to lyophilic salts. They can be easily precipitated or coagulated by the action of small amounts of electrolytes or by heating or even by stirring or agitating vigorously. The precipitated dispersed phase cannot be brought back into colloidal state by simply mixing it with the dispersion medium, unlike the lyophilic salts where it is very easy. Hence, hydrophobic salts are also called irreversible salts. Lyophilic salts and lyophobic salts differ in various ways. We can list out those differences in the table. We have seen lyophilic salts can be easily prepared, whereas it is difficult to prepare lyophobic salts. Because of the affinity between the dispersed phase and the dispersion medium, lyophilic salts are highly hydrated or solvated, which is not the case in the case of lyophobic salts. Lyophilic salts are stable due to hydration or solvation. Lyophobic salts are less stable, and as we have seen earlier, lyophilic salts are reversible, whereas lyophobic salts are irreversible. Visibility, an important characteristic here. The dispersed particles are not visible to the naked eye in the case of lyophilic salts. Even they are difficult to be detected under what is called an ultra microscope, about which we can see later. In the case of lyophobic salts, although they are not visible under or to the naked eye, they can be detected easily under an ultra microscope. A physical property like viscosity. Viscosity of a lyophilic salt is much higher than the dispersion medium, whereas in the case of lyophobic salts, it is almost the same as that of the dispersion medium. Surface tension. Surface tension of a lyophilic salt is much less than that of the dispersion medium, whereas it remains almost unchanged in the case of lyophobic salts. Charges on the particles, an important characteristic of salts. The dispersed particles have little or no charge on them in the case of lyophilic salts, and hence they do not migrate under an electric field, whereas the dispersed phase particles carry a definite charge. They may be positive or negative charges, and hence under an applied field they migrate towards the electrodes of opposite charge. Colloidal solutions may be further classified into three categories based on the type of particles as multi-molecular colloids, macromolecular colloids, or associated colloids or micelles. Let us first look at the multi-molecular colloids. All the discussion that we made earlier referred to the multi-molecular colloids, where smaller particles may be atoms, ions, or molecules aggregate together to give larger particles of colloidal dimensions. Hence, they are appropriately called multimolecular colloids. These species, which are small molecules or atoms or ions, are held together in the aggregate by weak van der Waals forces. We have the example of gold salt, sulfur salt, etc. A gold sol may contain particles of various size composed of several atoms of gold, that means dispersity. Similarly, sulfur sol consists of particles containing about 1,000 molecules. You have come across this sulfur sol. While passing hydrogen sulfide gas after the separation of the first group, you may find that yellowish precipitates appear in the solution in qualitative analysis, and you try to filter them, but you are not able to remove those particles which you felt they are there. It is because of the formation of sulfur sol under the given conditions when H2S is passed through the solution. Macromolecular colloids. We are familiar with the term macromolecules. The macromolecules means giant molecules where the molecular weights are very high, like proteins which are naturally occurring, rubber, a polyisoprene, again naturally occurring, or man-made polymers. All are giant molecules with large molecular weight. The dimensions of individual molecules are so large that they reach the colloidal dimensions, and hence they are called macromolecular colloids. So, when they occur in nature or when they are dispersed in a dispersion medium, the resulting colloidal dispersion is called a macromolecular colloid. Most of the lyophilic sols are macromolecular colloids. Examples, as I mentioned earlier, that of nucleic acids, starch, proteins, cellulose, gelatin, etc. In water, they form macromolecular colloids. And you can see here it is a single molecule consisting of thousands of atoms, and the size of this is in the colloidal dimension. And the third type of colloidal system is called the associated colloids or micelles. These are formed by substances which behave as normal molecules or ions when dissolved in water at low concentrations. That means they disperse to the ionic level, but when the concentration reaches a particular value, they start aggregating into systems of colloidal dimensions as shown in the figure here. You can see a molecule like this with a polar head group and the tail consisting of a long chain, say hydrocarbon. These molecules are called amphiphilic molecules, and in water they remain as individual molecules when the concentration is low. The concentration reaches a particular value which is called the critical micelle concentration. They form aggregates which may be spherical, may be elliptical, may be cylindrical, where the tail groups go to the core and the head groups are projected outside. The associated colloids are usually formed by surfactants, the surface active agents like soaps, synthetic detergents. These agents form micelles when present in solution at a concentration greater than the critical micelle concentration, about which we will discuss later when we take up the properties of colloids. Let me summarize what we have seen today. I started with the introduction to the colloidal state, crystalloids and colloids, how the substances are classified, and then realization that colloidal state, it is not the substance that we are interested in, characteristics of true solutions, colloidal dispersions and suspensions. Then we try to classify the colloidal dispersions into various types based on, say, physical state. We looked at what is the dispersed phase and the dispersion medium, based on which we classified them into sol, solid sol, aerosol, gel, emulsion, etc. And then classification based on interaction as lyophilic sols and lyophobic sols, and classification based on type of particles, in which we saw the classification into multimolecular colloids, macromolecular colloids and associated colloids. In the next lecture, I will discuss about the preparation of colloids and purification of colloids, because as synthesized they may contain large impurities which have to be removed in order to purify the salts.